Okay, good morning students. Today we'll learn about chapter 18, that is reflection and rotational symmetry. As you are already aware about the reflection, you might have studied in physics that reflection is a part of physics. In this process, when the light strikes a particular medium, it again returns to the same medium, and the process is called reflection. And because of reflection we are able to see different objects, right? So in this chapter we'll discuss symmetry, which is related with reflection. You've already learned this symmetry in your previous class. Now we'll see what the symmetry is about. Okay, so a figure is said to be symmetrical about a line L. Line can be of any name if it is identical on either side of L. In this case, L is called the line of or axis of symmetry, right? I'll explain this definition with an example. As you can see, this figure has a line segment AB, and it is being bisected by a line segment that is PQ, which is passing through O, right? So once this line segment bisect AB, it means these two parts are said to be symmetrical. Means one half of the part is equal to another half. It means this AO is equal to OB, right? So they are said to be symmetrical about each other. And the line which divides the figure into equal parts is called axis of symmetry or the line of symmetry. Means this PQ will be called a line of symmetry, right? Let's take another example. This example is about an angle. An angle is AOB or BOA, right? This angle is being divided by this line. This line this is actually a ray which is OC. So it is being divided or being bisected by this ray OC. So we can say that this portion of angle, that is COB and angle COA, they are symmetrical about this axis OC, right? In the same way we can consider an isosceles triangle. Suppose this is the isosceles triangle. We know that isosceles triangle has two sides equal. So an isosceles triangle is symmetrical about the bisector of the angle which is included between the equal sides. So these are the equal angles and this is the bisector. So we can say that this bisector line AD is axis of symmetry for this isosceles triangle ABC. In the same way we can consider the case of a kite. This is the kite. So the line of symmetry of the kite is vertical, because if you divide it, because this vertical line will divide the entire figure into equal parts. If you take the line of symmetry horizontally, which is passing through BD, then the two halves will not be equal. In that situation we cannot say that each part is reflection of each other or mirror image of each other, right? So a line which divides the figure into equal part and make two equal parts look like mirror image of each other or reflection of each other is said to be an axis of symmetry, right? Next example has been taken as a semicircle. As you can see in the figure, the semicircle is being divided vertically. So this line PQ is called axis of symmetry of this semicircle. In the same way we can take this trapezium. It is being divided vertically by a line FE. So this line FE is called axis of symmetry for this trapezium ABCD. We can also take the example of rectangle and a rhombus. As you can see in the rectangle, The rectangle has two sides equal and parallel, and the angle between the angle formed by the two consecutive sides is equal to 90 degree. So the line of symmetry for the angle can be taken as either vertically or horizontally. Means if this vertical line is drawn, it will divide the rectangle into equal parts. If this horizontal line is drawn, it will divide the rectangle into equal parts. So the line of symmetry for the rectangle is both horizontal and vertical line of symmetry. Right? Now we can consider the case of rhombus also. This is the rhombus. We know that rhombus has four sides equal. So the line of symmetry for the rhombus is through their diagonals. If the line is passing through CA, is this diagonal, it means it is dividing these two parts dividing this rhombus into equal parts. If we take this diagonal, another diagonal, like the line is passing through DB, then also it will be dividing the rhombus into equal parts. So we can say that the line of symmetry of the rhombus is through its diagonals. Okay. In the same way, we can consider the case of English alphabets. They can either have vertical line of symmetry or horizontal line of symmetry. As you can see in the figure, A is having vertical line of symmetry, B is having horizontal line of symmetry, C is having horizontal line of symmetry, D is having horizontal line of symmetry, E is having horizontal line of symmetry, H will be having both horizontal and vertical line of symmetry, I will be having both horizontal and vertical line of symmetry, M will be having only vertical line of symmetry, O will be having both horizontal vertical line of symmetry, T will be having only vertical line of symmetry, U will be having only vertical line of symmetry, V will be having only vertical line of symmetry, W will be having vertical line of symmetry, and X will be having both horizontal and vertical line of symmetry, and Y will be having only vertical line of symmetry. So there are different line of symmetry for alphabets. Right. Now based on this part, you can easily fill this exercise. This is just like MCQ questions. Let's try to fill this exercise. Okay, next topic is rotational symmetry. So first we'll see what rotational symmetry is about. In rotational symmetry, a figure is said to have a rotational symmetry if it fits onto itself more than once during a complete rotation. The number of times a figure fits into itself in one complete rotation is called the order of rotational symmetry. This definition can be understood with this example. Let's consider this equilateral triangle ABC. Now, three vertex of this triangle ABC has been marked as A, B, C. As you can see in the given figure, first this end of A will rotate and come to the position of B during the first rotation, and B will move to C and C will move to A, as you can see in this figure. After first rotation, when second rotation starts, this C will come to this point A will go to B, and B will move to C. Right, as you can see in the third figure. After third rotation, again A will move to its original position, B will move to its original position, and C will move to its original position. Right. So after 3 rotation, you can see that the vertex are in the same position as they were in the first figure. Right. So we can say that the order of rotational symmetry is 1, 2 and 3. Right. So this is about rotational symmetry. It tells how many times a figure is being rotated to move to its original position, and the number of times it rotates is known as its rotational symmetry, order of rotational symmetry. Right. Now let's consider an example of a square. A square is having 4 sides equal. So all 4 corners or vertex has been marked in the square, that is A, B, C, D. So after the first rotation, A will come to the position of B, B will come to the position of C, and C will move to the position of D. and again D will move to the position of A. After second rotation, A will move to this. A will move to the position of B, and this B will move to the position of C. C will move to the position of D. D will move to the position of A. Right. After the third rotation, C will move to the position of D. D will move to the position of A. A will move to the position of B. B will move to the position of C. C will move to the position of D. After the final rotation, that is fourth rotation, they will again come to their original places. Like A will come to the original place, the place where it started in the beginning. B will move to come to its original place. C will come to its original place, and D will come to its original place. So we can say that in this example, the order of rotational symmetry is equal to 1, 2, 3, 4. Means after 4 rotation, it is coming to its original place, right? So from these two examples, we have concluded that when a figure is regular, means when all sides of a figure are equal, then we can say that the order of rotational symmetry depends upon the number of sides. As you have seen in the triangle, equilateral triangle, there were 3 sides, so rotational symmetry was equal to 3. As in this case, a square is having 4 sides, it means the order of rotational symmetry is equal to 4. So if we take a regular pentagon with 5 equal sides, then their order of rotational symmetry will be equal to 5. In the same way, when regular hexagon is taken, then the order of rotational symmetry will be equal to 6, and so on, right? So whenever you have been given a regular figure, that is a figure with all sides equal, then you can say that the number of rotational symmetry is equal to the number of sides. As you can see in this example, if we rotate the adjoining figure through angle 90 degree, 180 degree, 270 degree and 360 degree, then each time the figure will fit exactly onto itself. Thus the given a figure has a rotational symmetry of order 4, right? It means it's having 4 sides, so the order of rotational symmetry is equal to 4. In this example, each of the letter H, I, N, S, O, X, Z, they are having rotational symmetry of order 2, since each one of these letter, when rotated through 180 degree and 360 degree, they will fit exactly onto itself each time. So if I rotate this figure by 180 degree, it will come to this position. If I rotate this figure by 180 degree, it will come to this position. If I rotate this figure by 180 degree, it will come to this position. And again, if it is rotated to another 180 degree, means 360 degree, then it will come to its original position. That is why the order of rotational symmetry for these given figures is equal to 2. Since this figure is having 3 different closed figures, so their order of rotational symmetry can be taken as 3. Right. So from the above discussion, we can say that a square has 4 lines of symmetry, namely the diagonal and the lines joining the midpoint of opposite sides. Also, a square has rotational symmetry of order 4 when rotated through angle 90 degree, 180 degree, 270 degree, 360 degree. A rectangle has 2 lines of symmetry, namely the line joining the midpoint of its opposite sides. An equilateral triangle has 3 lines of symmetry, namely the bisector of its interiors. A line H has 2 lines of symmetry. An isosceles triangle has a line of symmetry, but it does not have rotational symmetry, right? So with this conclusion, solve these questions, that is solve the questions from exercise 18.18b. Okay, and if you have any doubt, just clarify your doubts. Thank you.